All right, so our next lightweight phenomenon is called total internal reflection. So what this is, light is literally going to stop passing through a surface and completely reflect off the boundary. And this only occurs at an angle known as the critical angle, and any angle larger than that critical angle. So anything below, it's not going to work. Once you hit that critical angle or higher, that's when it'll happen. This is only going to occur when light goes from a larger index of refraction to a smaller one. So essentially, you're going from something that is more dense to less dense, okay? So for example, you have this piece of glass here. They are shining in some sort of light, and it is completely getting reflected in the material here. Likewise, this is happening here as well. It is completely getting reflected within that material. Okay, so reflection and refraction. Refraction does not exist at 90 degrees, so that'll never ever happen. So when the angle of incident equals the critical angle, the angle of refraction is 90. Obviously, we just said this, refraction is not occurring at that point. However, when the angle of incident is greater than the critical angle, all light undergoes reflection, right? So this is only going to exist when light is moving from a larger density to a smaller density material, okay? How we can kind of prove our total internal reflection formula. So we start out with Snell's law right here, okay? So this is nothing that's kind of new. So this is Snell's law. However, because we know that in refraction, uh, it's happening at 90 degrees, this becomes 1. So I can put a 1 there. So then I really just have n1 sine of the critical angle equals n2. We want to isolate the sine of the critical angle, so we divide n1 on both sides. So now we're left with this ratio, n2 over n1 equals sine theta of the critical angle. To find the critical angle, we use the inverse sine. So here we get our critical angle is equal to the inverse sine of the ratio n2, or your index of refraction of the material 1 over material 2. Again, we just plug into our calculator, make sure it's in degrees, and we're all good to go. Now we're going to talk about this phenomenon called dispersion. So I'm sure you all have seen a rainbow at some point in your lives. So this is the spreading of white light into the colors of the rainbow due to various differences in wavelength, okay? The red light is going to bend the least, and blue light, or violet light to be more specific, is going to bend the most, okay? So if I look at this image, as we could tell, my blue light, look at this, it bends the most, whereas my red light does not appear to do that so much. So there is definitely a difference of that angle, right? So blue light's going to refract more than red light due to the difference in wavelength. This is going to cause the blue light to deviate from its original path by a greater angle than the red light. Okay, we can see that in the picture. So we call this chromatic light, which is also considered white light. Okay, what is chromatic light? Well, it is just white light that is the combination of all the colors in the rainbow. So hopefully you've heard the term Roy G. Biv. Okay, Roy G. Biv is kind of just a little acronym, right? Red, orange, yellow, green, blue, indigo, violet, all the colors in the rainbow. Okay, once it goes through a glass prism, right? You shine white light through a glass prism, you will see Roy G. Biv, the colors of the rainbow come out. Okay, but they will be their own separate bands of light. Okay, so we go from chromatic light to monochromatic light, which means that we're a single color. That should make sense because we have single colored bands of red, orange, yellow, green, blue, indigo, and violet, our Roy G. Biv. They're their own separate bands, okay? Whereas our white light was chromatic, it was a combination of all of these things, okay? So the term, the prefix mono just means one, okay? So it's like one single color. Okay, so their own bands, it's not a mixture anymore. Okay, so if you've ever had this opportunity, I would suggest getting a glass prism, or sometimes if you have like your front door, sometimes the way the light shines through it, it will kind of serve as a glass prism. I know growing up in my house, that's what it looked like, and I did see like rainbows on the wall often. And at the time, I couldn't explain it because didn't understand what dispersion was since I was a little child, but it is a very cool phenomenon to see. And this actually works with our rainbows that we see in the real life. When uh in our skies, right, when it rains, you have a raindrop, and so that's what it's getting. It's the white light or chromatic light is going through these raindrops, and then you see these rainbows, right? That's why we see that bending, that nice curve. So let's take a look at this question. In which diagram below could the light source and optical device be used to demonstrate the phenomenon of dispersion? So first of all, we know that it cannot be going through a square piece of glass. That's not going to work. Even sunlight through a square piece of glass, that's not going to work. So now we're left with two options. So it says monochromatic. Okay, remember monochromatic was the single band colors. So that means that we started out with Roy G. Biv already, and that cannot be true. So this is not the right answer. So let's make sure that D is the answer. So we consider sunlight to be our chromatic white light right here. And what that means is that when it passes through that glass prism, your, Roy G. Biv, so Roy G. Biv is coming out on the other side. Okay, so choice D or choice 4 is the answer here. Okay, there's also a mathematical relationship between a ray and different media. Okay, we say that the index of refraction, n, is inversely proportional to speed and wavelength, as we can see here. This formula is in your reference table. It's just setting up ratios. Okay, that's what that is. So because we have things on denominators, we obviously know that they're going to be inversely proportional. So if one of those denominators gets bigger, then that means that my index of refraction is going to decrease. Okay. So now let's talk about what happens when a light ray re-enters the same medium it was originally traveling in before or after it had traveled through a different medium. So, right, so this is N1, the glass is N2, and then we go back into N1. So what we say happens here is your refraction is always going to be accompanied by reflection. That's just non-negotiable. Okay. When a light ray enters back into the same medium it originally started out in, the light refracts back at that original incident angle from the original medium. So basically, this angle I up here is going to equal this angle E. We know that angle I is going to be different compared to angle R because that's my refracted angle. But the idea is that the angle you started out in terms of your incident angle is going to be the same as your angle coming out because you are going back into the same medium. Okay, so let's talk about transmission, reflection, and refraction. Which diagram best represents the behavior of ray in monochromatic light and then in air incident on block of crown glass? Okay, so we're going from air to glass. Okay, so which example? First of all, we know that there should be three things going on. There should be reflection and refraction, which is essentially the same thing as transmission. Okay, transmission, that means it just goes through the material. Okay, so I'm also going to have an incident ray. That's non-negotiable. I will always have an incident ray. So let's see. I need to have 3 rays on my diagram. That's what I'm looking for. That's going to give me the correct answer. So A, I only have 2 rays. No good. Same thing here. I only have 2 rays. No good. Let's see. Let's take a look at choice B. So they're saying that it gets reflected in the material and gets refracted in the material. And reflection goes like this. It goes off of the material. Okay, so it bounces off that boundary point where glass and air meet right here. So this ray is incorrect. So therefore choice D is correct. We have my incident ray. This is my reflected ray. And this is my refracted ray. So choice D is the answer. That's pretty much what light wave phenomena is going to be like.